This video provides only a general overview of physical chemistry and explain in simple terms on why the reactions occur. We will look into the thermal chemistry, into equilibria chemistry, and into kinetics chemistry, and we will combine all of them together in order to conclude why do some reactions happen and why not. I find it quite interesting, so I'll try my best to explain stuff to you guys. Today's topic is why do some reactions occur and some don't. We will specifically discuss which reactions occur, why do they occur, how do they occur, and how fast do they occur. We're also going to describe it mathematically, as you will see. But before that, we need to go into supplementary topic from year 12 in order to just refresh our mind on some heat transfer and enthalpy changes. So as we remember from first law of thermodynamics, energy cannot be created nor destroyed, it can only be transferred from one form to another. This is important because each reaction emits heat or consumes heat, and we need to understand that none of this energy is created during reactions nor it is destroyed. Okay, so also we need to assume that change in heat at constant pressure is the same thing as enthalpy. We don't really need to know why, because it's a bit of a deeper discussion. However, we just need to assume that, yeah? Yeah, but the main relationship we need to know about is that if the pressure increases, then delta H will be also increased. As you may remember, for exothermic reaction, our delta H is negative because we emit energy. We go from higher energy reactants to lower energy products. And in endothermic reactions, we go from lower energy reactants to higher energy products. So we need to input some heat or energy into our system in order to make it happen. Yeah, so right now we're gonna move on to the calorimetry. And if, for example, our reaction goes at a reasonable rate at the room temperature, we can basically use calorimetry in order to calculate the heat required or emitted during a certain reaction. So let's say that our system will be the test tube and our calorimetry will be our surroundings, yeah, as before. And we will basically measure the amount of heat given in, or given out. So yeah, here you may see a formula of our heat basically transfer, and it is dependent on the specific heat capacity of the basically our calorimeter. For each calorimeter, would it be, for example, a polystyrene cup, or will it be, for example, water, like in our example? The main point is that every calorimeter has its own CS. It is the amount of heat required to raise a specific calorimeter by 1 degree Celsius. So let's imagine that we don't really have a CS number for our calorimetry, which is in our example is just water. Before we start our experiment, we need to get this constant. And what we are doing, like in most of the cases, we calibrate the calorimeter. And we do it by applying the specific amount of known energy and just looking at how the temperature will be changed, yeah? And then we just work out for the CS during our formula, and that's basically it. Then we can start working on our reaction. Okay, let's say that we have calculated our CS of our calorimeter. In this case, it's 29.7 kilojoules per Celsius. And when 8 grams of methane combusted, the change for temperature was plus 15 Celsius. Yeah, but in this case, we got our delta Q of calorimetry. Yeah? However, we need, in order to calculate the amount of heat given out by a specific reaction, in this case methane, we need to make it delta Q of the system. Yeah, and as we know, energy can be destroyed nor created, so Q of surroundings equals to minus Q of the system. Yeah. Then we just switch the sign and calculate our delta H. And here we specifically just calculate the enthalpy per mole of CH4 combusted. So that's why we divide by the amount of moles. Now let's talk about phase changes. During phase changes, our temperature of the substance does not change significantly because our thermal energy is used not to raise the temperature, but to break the bonds. Let's imagine that we want to calculate the amount of energy Q to raise 90 grams of water from minus 20 to 50 degrees. Because we go through those phase changes and we need to use different formulas each time. Because when we don't have delta T, we cannot use the first formula on the top. However, we can use the third one on the bottom. And that's what we are going to do right now. each time we are going through the phase change, we need to use different delta H because it's like from the tables. In order to go from liquid to solid, we need delta H of fusion, and in order to go from liquid to gaseous state, we need delta H of vaporization. Here is a different example with formula which accounts for the mass of our H2O of our calorimeter. The formula is the same, we just adjust our Cs and M. Delta H is calculated just as normal. Just remember to make sure that you're not switching up the mass of calorimeter and the mass of basically reactants. Now we will discuss what makes a reaction go. The reaction between magnesium and oxygen is strongly exothermic, so delta H is negative, meaning that the heat is given out, yes? We can represent this by the energy diagram, so here. And we can see that the products are lower in energy than the reactants, and the energy difference between them is negative. We often say that the products are more stable than the reactants. In this context, more stable means lower in energy. It would be very tempting to conclude that the magnesium oxide is formed from magnesium and oxygen because magnesium oxide is more stable, is lower in energy than magnesium plus oxygen themselves. However, even though it may be very tempting to think that way, we can see an example of dimerization of nitrogen dioxide, where we can see that reactions can go forward and backwards, down the energy level and up the energy level. So it does not really cohere with the fact that spontaneity of the reaction depends solely on enthalpy. As we can see here, it is not about making the product lowest in energy. Even though it matters, we can clearly see that it is something different which influences the spontaneity of the given reaction. The second law of thermodynamics allows us to predict which processes will go and which will not. It is therefore the key to understanding that what drives chemical reactions and what determines the position of equilibrium. The simplest description of entropy is to say that it is a quantity associated with randomness or a disorder. For example, a gas has a much higher entropy than a solid, as in the gaseous molecules are free to move, while solids are not. Perhaps most of you have heard something like entropy always increases. The idea is that any process which takes place is always associated with an increase in entropy, that is, an increase in chaos or disorder. However, thinking about that, let's imagine water going into ice. The entropy is clearly dropping. So what's going on here? Here is another example with NH3 and HCl. From two gases we form one solid, which is a drastic amount of decrease in entropy. And so we need to adjust our previous statement. Entropy of the universe increases in a spontaneous process. Even though the entropy of this system decreased drastically, in order for this reaction to be spontaneous, delta S of the universe total should be positive. So we can see clearly here that delta S of the surroundings compensated for that massive decrease in entropy of the system because this reaction is exothermic. So reactants were from on a higher level, went to the lower level, they emitted a lot of heat to the surroundings, and by increasing the temperature of the surroundings, we increase the entropy because we increase the kinetic energy of the molecules around, they move faster, and there's basically more quanta of energy there. So now we understand that in order to answer the question which reaction goes, we need to answer when delta S total is bigger than 0, yeah? And in order to answer this question, we need to talk a little bit more about the delta S of the surroundings. We need to understand that we experimentally derived that heating a cool object increases its entropy more significantly than heating a warm object with the same amount of heat, yeah? And by doing those experiments, we derived the formula. Delta S of surroundings equals to the heat absorbed by surroundings divided by the temperature. So clearly there is some relationship between the temperature and delta S of surroundings. So let's substitute our new definition into the previous delta S total formula that we had. And now we can understand what really influences our spontaneity. But before that, we need to understand that Q absorbed by the surroundings is the Q lost by the system. And that's why sometimes you can see a formula written by delta S of surroundings equals minus delta Q divided by T, because they are using delta Q of system. Now let's talk about the second part of the equation, delta S of the system. Delta S of a system will be basically the entropy, molecular entropy of the reactants minus products. Yeah, so it's just like with enthalpy. You are not expected to know what like experimentally they do in order to calculate those molecular entropies. So just trust me on that. And here on the bottom you can see me calculating the spontaneity of the same reaction of ice forming from liquid water. And as you may see, the only factor that affects spontaneity is temperature. For the convenience of your future life, we will use Gibbs free energy instead of delta S of universe. Basically, the trend for the spontaneity is going to be the reverse of that one that you have seen with delta S of the universe. Negative delta G will inform you for the fact that the reaction is spontaneous. So if delta G is negative, it means that the products have lower Gibbs energy than the reactants, and this is the driving force for each reaction, basically. Okay, so since we have already talked about which reactions go and which don't, now we need to describe how a reaction basically goes. Let's get back to the reaction of dimerization of nitrogen dioxide that we have talked about before. It's a reverse reaction where a certain equilibrium position is reached each time. So we can start from the reactants and reach equilibrium, and we can start from the products and reach equilibrium, yeah? And the equilibrium basically dictates where our like endpoint of our reaction lays, yeah? Now we will discuss like quite an important point, yes? So why does delta G drops to the equilibrium? So there is some connection, mathematical purely, that you can see between the randomness and equilibrium constant, yes? However, I want you to understand it theoretically. Suppose you have a container with 100 marbles. If 100 of those marbles are red, yeah, then the amount of positions you can place them randomly is a lot smaller than if you were to have 90 red beads and 10 yellow beads. So having not a pure substance increases the amount of randomness, like the amount of positions you can discretely position those molecules in space. And as we know, by the second law of thermodynamics, universe tends to go into the more of a disorder, yeah, state. And right now we will basically describe this relationship mathematically as we should, yeah? K is an equilibrium constant which basically shows us the proportion of products and reactants at equilibrium. K is constant at a set temperature, and if let's say K is bigger than 1, then we can say that equilibrium favors products, because at equilibrium there are more products if it's like more than 1, and if K is less than 1, then it favors basically reactants. Now let's talk about Q. So imagine we are mid through the reaction, yes, at point P1. At this point P1, we have a different proportion than at equilibrium. And we are basically using Q to describe the amount of products and reactants anywhere else but at equilibrium point. It just makes it convenient to describe the position at equilibrium. Suppose at P1 we have added to the system more reactants, yes? And we will just basically describe that at P1 we will tend to go back at equilibrium. So our system will try to go back to equilibrium. Another way to describe it is that our Q will try to become our K. Yeah. Here I drew a simple graph on the bottom here, and you may see the spike going down because the Q, our proportion changed because, for example, we added our reactants in this case. That's why it went down. But since our K is constant, our equilibrium constant, equilibrium didn't shift anywhere else, and through time you see this red, like, sorry, not red, purple line going back to equilibrium. And at P2 we have more, for example, products, Yeah, we added products to the system, and it goes back down to the K. So it's basically Le Chatelier's principle, if you know what this means. But if you don't, just don't worry, we will describe it later. Okay, nice. And now we will talk about the connection, mathematical connection between delta G and the equilibrium constant. You don't really need to know the proof of this equation, and because it's quite hard, it involves calculus and all of that, like it goes deeper than we should. There is nothing more I can tell you from my side, so just look at the equations until they make sense to you. However, I'll just show you this graph that which I found on the internet, which might be helpful for you to understand this topic. So yeah, just take it. And here we also have an interesting fact that basically, even if delta G of reactions is bigger than zero, we go from lower Gibbs free energy reactants to higher energy Gibbs energy products, we still have some reaction going, yeah, because those lower energy Gibbs free energy reactants will still go to equilibrium, but the equilibrium is so far on left that it's not really visible or detectable by any apparatus, yeah, but it still goes there. So just make sure that you understand that even though reaction has positive delta G, it does not necessarily mean that it won't go, yeah, to equilibrium. Okay, and now we will describe Le Chatelier's principle mathematically. We will basically combine those two equations from before into one very beautiful one. So, and it will show us how basically equilibrium position shifts with changes in temperature. And we will basically show it in a graph later on. Yeah, but basically, the sign of delta H determines how K will depend on temperature. If we were to have a endothermic reaction, then increasing temperature will result in K becoming larger, so we will favor more products. And as you may see, we are fooling around with K, so we are shifting equilibrium point. So just think about the graph, we're gonna look at it later, of course. To make it easier for yourself, in each reaction, just place Q. If endothermic reaction, you place Q on left side of equation. If it's an exothermic, you lose energy, so you place it on the right equation. And as Le Chatelier's principle said, system tries to counteract the change, so if you will increase temperature, the reaction will go through the direction to decrease temperature, so we will go the exothermic pathway, yeah? So just play around with that thing. Okay, so we have gone through actually a lot of stuff right now. We have discussed which reactions go and where do they go, yeah? So now let's discuss like how fast do they go to where they should be going, yeah? Because we could have thermodynamically feasible reaction, however, it may take a lot of time to reach the equilibrium, so for us, this reaction is not like visibly spontaneous, yeah? So just we'll play around with activation energies and Arrhenius equation. But before that, let's basically discuss on what dictates the rate of the reaction. And the only thing that you should be looking at is how molecules are colliding, yeah? So here you may see, I will clearly summarize some of the main concepts that you need to understand, and we will basically later on describe them mathematically in something called Arrhenius equation. So we will basically see the dependence of the rate on something of concentration or the pressure. Concentration, pressure is the same thing, because if you will decrease concentration by decreasing the volume, the number of molecules didn't like the number of molecules per unit volume changed, so we increased concentration. So that's why I'm referring to pressure and concentration as the same thing. speed, size, and correct orientation. That's quite interesting, so you can just read about it more if you in your free time, so if you wish. And last but not least, activation energy and basically energies of molecules. We will see quite soon that the rate is determined by the activation energies. And you may ask yourself a question, why is there is an energy barrier in the first place? So imagine we start with a block stood on its short side and then try to push it over so that it lies on its long side. The end position has lower gravitational potential energy than the starting position, yeah? But to push the block over, we first need to tilt it on its edge, and in doing this, the center of gravity rises, thus increasing the potential energy, yes? So that's the analogous thing right here. At the top of the profile, called the maxima point, there is a suggestion as to what the transition state might look like. The carbon atom is 5-fold coordinated with partial bonds to the incoming OH- and the departing Br-. It is, it is important to realize that there is no way we can guess at the precise structure of the transition state. All we can do is speculate about its general form. It is clear from this picture that the energy has to rise when the transition state is formed. The bonding is far from optimum, that's the problem. But that's not the only problem, because there are also the partial bonds made between OH and the carbon and Br. This unusual geometry and the presence of partial bonds is typical for transition state. And it is not really surprising, therefore, that this energy is much higher than the energy level of the products and reactants, of course. Uh, However, not all reactions have an activation energy. As you may see, like lithium and fluoride form salt here, and because they don't really have a lot of repulsion and like this geometry stuff happening on, they don't really have anything being broken, so we don't really need energy input, yeah? Yeah, so just basically think about all of the factors that we have talked about collision, yeah? Okay, guys, so let's get into the description of the rate. Let's derive the rate. So for any elementary reaction, so elementary which goes as it's written down in the equation, we can assume that the overall rate is the same as the rate of consumption of a reactant or rate of formation of products, yeah? However, we can describe rate in a different sense. We can derive rate in terms of concentrations of reactants, yeah? And in order to do that, we actually need to derive an experiment, and only experimentally we can get something as written here on the bottom. So here you see that the rate is dependent on the concentration of the reactants and some constant K, about which we will talk about right now. Okay, so the K, the rate constant, is basically a mathematical description of the collision theory that we have already talked about, yes? K equals A multiplied by the E, yeah? And there are two parts for this formula. The first part is the A part. A part applies for the geometry of the molecules, and the second part applies for the number of molecules with energy greater than the activation energy. So basically those two constants, and they are specific for each reaction. Both pre-exponential A constant and the second part with E depend on temperature. However, the second part depends on temperature like much more significantly. So we just can omit the fact that A is also dependent on temperature. Okay, here are some graphs which may help you to describe the relationships, make it clearly visible how change in temperature, activation energy, and all of that will change our rate constant. And here we need to understand that if we will increase the number of the small k, this green k, we will also increase rate because we are multiplying by the bigger number, yeah? First graph shows that increasing temperature increases the amount of molecules with energy more than or equal to activation energy, and that happens because this thermal energy, increasing temperature, increases the kinetic energy of the molecules in the system. They collide faster with a higher speed, and they basically have higher energy on average, yeah? The graph number 2 shows you the same absolute thing. As you may see, that higher activation energy decreases the rate because we have a higher energy barrier, yeah? And absolutely the same thing with a different plot. As we increase activation energy, rate decreases. But however, if we will increase the temperature, we will divide this activation energy by a bigger factor, so it will be less basically important. Okay, guys, so let's talk about on how to predict our rate laws equations. Yeah, we have two types of reactions. Elementary reactions, they are basically the simplest reactions that take place as written, and we have complex reactions. Those are set of elementary reactions going one after another. The problem is that we can use elementary reactions to predict the rate law for a single step. However, we cannot do the same thing with the complex reaction. Here on top we can write that rate equals to the K multiplied by H and Br concentration. We can do the same thing for each of the steps of the complex reaction that we have on the bottom. However, we cannot really do this and generalize this and write that the rate of this reaction is K multiplied by O3 squared. Yeah, you know what I mean. And how do we actually get those rate laws for those complex reactions? Only experimentally. You need to remember this. Yeah. Okay, so let's look at an example right here of nucleophilic substitution. And here in the middle we have two reactions and one intermediate formed. Yeah. This intermediate is also positioned at minima, just as reactants as products. Yes. We have two transition states, and the first activation energy is higher than the second activation energy. Yes. And this gives us clue to which step is slow, which step is rate determining step. Rate determining step is the step which basically allows us to predict the rate of the equation. So if the rate of the slow step is 0.2, then the overall rate is also 0.2. Here I have rewritten the equation and we have two steps, yes? The first reaction and the second reaction. The first reaction, both of them are elementary reactions, yes? And since the first step is slow step, we can take its elementary step and use it to determine our rate law, yeah? And overall rate for this reaction of those two steps will be that on the middle of the screen. However, one thing to notice is that even though we use words such as slow and fast, both of them occur at the same rate because our slow step is limiting our fast step. Because our fast step can't go as fast as it could go because our first step is slow. It's quite tricky, but I think you'll get there soon. Okay, so let's talk about reversible reactions. The one thing you need to know is that every reaction is reversible. However, the extent of reversibility is dependent on the position of the equilibrium. We have described it like previously using this graph, and we have two reactions here. Reaction 1 has equilibrium somewhere more to the middle at a set temperature, and so we call this reaction more reversible. And the reaction 2, which has an equilibrium constant far to the right, is being called as to going to completion. Yeah, but now let's look at it a bit deeper. So we, for example, have a reaction of A, B going to C, D. Forward reaction has its own Kf, and reverse reaction has its own Kb. Yeah, so K forward, Kb backwards. Here is actually a proof of derivation of the equilibrium constant, because at equilibrium rates are equal, so we can derive our K equilibrium. And here we can use Arrhenius equation in order to determine the effect of the reaction being exothermic or endothermic. In this case, delta E, delta energy, is very, very similar to delta H. However, they are a bit different thing. We can basically understand them similarly. So that might be basically useful if you know the activation energies for both the reverse and the forward reaction, but don't know the enthalpy of the reaction, yes? What we actually got with that equation is that it tells us that the equilibrium constant varies with the temperature in a way determined by the value of delta E, the energy change for the reaction. If delta E is positive, an endothermic reaction, an increase in the temperature results in an increase in the equilibrium constant. In contrast, for the exothermic reaction, which has negative delta E, increasing the temperature reduces the equilibrium constant. Yeah, so if we identify delta E with delta H from our bottom equation right here, which we derived a bit earlier, we can basically see that that's all comes up to a mathematical description of Le Chatelier's principle, yes? So in that sense, we used equilibrium, and in that sense, we used more of a delta G approach, more of the like Gibbs free energy approach type of, yeah. As you may see, we can go around like and follow up with combining those two equations, but I find it quite useless right now for us. Okay, and right now we are ready to discuss something called pre-equilibrium. Pre-equilibrium is an assumption which will help us to identify the rate law for a complex reaction of whom second step is slow. So not the first step as we have seen earlier, it is an easier variant of this case, but now the second step is slow. And how do we know it's slow? Because we have a rate law which was determined experimentally. So we have an experiment going on, and experimentally we got this relationship. And basically this relationship of K gave us an idea about a mechanism, yeah? You are not expected to predict the if a step is slow or fast based on the rate law, because they're like specific people that do it for money. So let's say that some smart guy just came up with an idea that the second step here is slow, yeah? And here our pre-equilibrium assumption goes. Before the slow step, step 1 has to be at equilibrium in order for us to be able to derive the rate law. Since we have assumed that our first step is at equilibrium before the second step, we can write the equilibrium constant, and we need to solve for the concentration of the intermediate. You're gonna get it soon. So we solve it for the concentration of an intermediate and stick it into the rate law for our slow step. This will get us the rate law with the relation to the reactants and only reactants. Because we have a problem, we cannot really have an intermediate included in the overall rate law. And here, as we may see, we have predicted our rate law successfully, just as experimental one. And that's how we basically prove mechanisms, yeah? Here, you may see that the pre-equilibrium assumption is only valid on the second graph, because in the second graph we have first activation energy lower than the second activation energy. And basically, yeah, that's it. That's just for you, for convenience, and that's it. Thank you. Okay, and the last thing we call apparent activation energy. Before that, for any given reaction, we know that we can determine activation energy by measuring how rate constant K varies with temperature, yeah? That's quite useful to know. We just fitted everything into the Arrhenius equation and just solve for activation energy. However, for complex reactions, we also may need to find some sort of a relationship between the activation energy of the elementary steps and the whole complex reaction. For a complex reaction of whom the step 1 is slow one, we have assumed that rate is equal to the rate law of the first elementary reaction, yes? So in this case, our apparent activation energy equals to the activation energy of the step 1, yeah? This can be seen on the graph 1, yeah? However, on the graph 2, we have the second type of reaction where second step is our slow step. And in order to calculate our apparent activation energy, we need to use all of those activation energies and we need to find this relationship between them. And I'm going to show you how to do it right now. The way it is useful is just basically speeds up a lot of, like, saves us a lot of time during our calculations, if any, you know. And that's basically it. This might not be the most useful thing, but that might be also interesting for you maybe. So I'm just showing you this in case, you know. So thank you for watching my video. Maybe the last slide was not really important for you guys. However, it might be important in the next video on physical chemistry. So why do chemical reactions happen? So the easiest part is just by saying that the entropy of the universe increases with the reaction. Then why does the particular chemical reaction increase the entropy of the universe? We may ask, and then we may say that for endothermic reaction it must be because the entropy change of the reaction is positive. However, for majority of reactions the answer will be because the reaction is exothermic, yes? So we give out heat to the surroundings, thus increasing the entropy. So we compensate for that decrease in the delta S of the system. How can we make the product we want, yeah? If the reaction is favorable, all that is needed is to supply enough energy and basically by varying the temperature, yes? However, if the reaction is not favorable, we will look at the next video. We can couple some reactions with more favorable. So that happens in biological system, for example. If the reaction is unfavorable, for example, products are higher in energy than the reactants, we will need to couple it to another reaction which is strongly favored, or simply not allow the reaction to come to equilibrium. Interesting, guys, but as I said, everything comes in the next videos. So thank you for watching, and I'm glad that you watched until this point. Thank you.